Okay, so let's talk about complex numbers. This is a review of complex numbers, and there are some new things you have if you haven't seen already. So we are going to go through them. Okay, so first of all, what is complex number? So we already know what real numbers are. So we know that okay, we have zero. Then we have natural numbers like 1, 2, 3. Then we have negative numbers like -1, -2, -3. These are also called negative integers. Then we have fractions like 1/2, 3/4, minus 7 by 5, 3.5. Those are all fractions. Okay, and these are actually called rational numbers, but let's not go into that. Then we have irrational numbers, for example pi, √2, √3, etc. that if you cannot exactly represent them in decimal forms, they go on and on forever without repeating or anything, right? So these are our irrational numbers, and all of this combined is what we call real numbers, right? And we have seen like a real number line, like we have 0 here, 1 here, 0.5 or 1/2 here, right? Then we have 2, 3, 4 here. √2 is somewhere around there. Then we have -1 here, -2 here, etc. And this goes on forever. So we have seen this real number line. And these things were very common in your HSC and stuff. Okay, so you should be familiar to these things. Then we were also introduced to something called imaginary number. Okay, so if you remember, square root of -1. So we know that square root of 4 is 2, right? So if you square 2, you get 4, right? If you square 9, you get 3, and if you square √2, sorry, I meant square root. You meant square. You square √2, you get something like 1.41 something, right? That doesn't repeat and goes on forever. So we have seen, okay, you can square root positive terms, but we exactly didn't know how to square root negative terms, and does that even make any sense? So that was the question actually asked by a lot of people in early stages of complex numbers, and people actually used complex numbers and imaginary numbers as just a math trick. Okay, so they thought that okay, it just works, we don't need to think about it very much, just let's call √(-1) as I, and let's just use it to solve things. That's that. It was just a trick, mathematical trick, and everyone used it like that. But later it was kind of mathematicians kind of made rigorous basis for that, and etc. And everyone started to accept that okay, yes, negative numbers can be square rooted. Okay, there is a meaning to that, and we will see that here, don't worry. But first let's talk about what are imaginary numbers. So imaginary numbers, well, this is the original imaginary number, but you can always multiply things with that. So for example, if I ask what's the square root of -3, well, you can ask, well, this is just -1 times 3. So I can say, well, this is √(-1) times √3, meaning this is let's write I first. So this is just I times root over 3. Okay, so this is like root 3i. Or if I had asked you minus 9, you'd say, well, this is root over 9 times I, or 3i, right? So these are called imaginary numbers, something times I, right? So b times I, where b is any real number. This is called an imaginary number. Okay. And what we call a complex number is basically a mix of both real numbers and imaginary numbers. So in general, a complex number looks something like this. It has an imaginary part and has a real part. Okay, so this whole thing is called a complex number. And complex numbers are basically a general superset of real numbers in a sense. Okay, so kind of real numbers are just a subset of complex number, and there are higher structures, but for now we are interested only in complex numbers. So we have seen real numbers represented by a line. Are there any visual pictures for complex numbers? Well, yes, there is. What we do is we already have real number, and we actually use another axis perpendicular to that, perpendicular to the real axis, and this is called imaginary axis. And we use I, twice I, and on the bottom we have minus I, minus 2i, etc., and it goes on forever. So in a sense, imaginary number gives a new dimension to our number system. Okay, so every point here has a meaning. For example, let's say this point here, which is 2 away from the imaginary axis and 2 away from the real axis, is 2 comma 2 in I guess if you were using the Cartesian system in a graph, but we will write it here as 2 plus 2i, 2 plus 2i. So this point here is 2 plus just 1i, right? So this is how we use complex numbers, and this is how we represent them in a plane. This is actually called the Z plane, or Argon plane or something. Okay, so let's just call it Z plane, right? So this is how we represent a complex number, and this is going to be somewhat important for us right now, even though this is just a review. Next, let's move on to how we add to complex numbers. Okay, so how do we add to complex numbers? For example, let me give you two examples. 3 plus 2i plus, if I say like minus 5 minus plus, let's say, I don't know, 5i. How do we add them? Well, we add them just like our normal numbers. 3 plus 2i, then we have 5 plus and minus, so we have minus 5, then we have plus times plus, that is plus 5i, and if we add them up, we have 3 minus 5, so minus 2, 2 plus 5, that is plus 7i. So this is how we add to numbers, to complex numbers. How do we subtract them? Well, 3 plus 2i minus 5 plus 5i. If we subtract one from another, we have 3 plus 2i, minus times minus gives us plus, minus times plus gives us minus, and 3 plus 5 is 8. 2 minus 5i is minus 3i. So this is how we can add two complex numbers to get another complex number. Okay, then how do we multiply two complex numbers? Well, so this is we multiply two complex numbers. Well, we have 3 plus 2i times minus 5 plus 5i. Okay, so we have 3 times minus 5 minus 15, 3 times 5i, that is plus 15i. Then we have 2 times 2i times minus 5, that is minus 10. 2 times minus 5 minus 10i. Next we have 2 times 2i times 5i, so plus 10. We have 2 i's here, so 1 i here and 1 i here, so we have I squared. And if you can remember, our definition of I was root over minus 1. That means I squared equals to minus 1, right? So we can substitute I squared for minus 1. We have minus 15 plus 15i minus 10i plus minus 10. And we have 15 minus 15 times minus 10, this is minus 25, and 15 minus 10i is plus 5i. Okay, so this is how we multiply two complex numbers. And how do we divide them? Well, that's also quite simple. 3 plus 2i divided by minus 5 plus 5i. So what we do is multiply top and bottom by their something called complex conjugate. Okay, so that's going to be an important part of our circuit course. So how do we complex conjugate something? Well, we just negate the imaginary part. So the complex conjugate, so let's talk about the complex conjugate first. If we have a complex number, let's say 7 plus 8i, then its conjugate is 7 minus 8i. So notice the real part stays the same, okay, but the sign in front gets changed to minus. And if the sign was negative, so maybe 7 minus 8i, its conjugate will actually be 7 plus 8i. So we just change the sign of the imaginary part, right? And there's an interesting fact that if we multiply z times its conjugate, we have 7 minus 8i times 7 plus 8i, and if we multiply them all together, we have 7 times 7, 7 squared. Then we have 7 times 8, 56i, minus 8 times 7, minus 56i, minus 8 squared, I squared. And if you can see that the 56 cancels out, we have 7 squared minus 8 squared, and we know that I squared equals minus 1 from previous logic and the definition of I. We have 7 squared, so we have minus times minus plus 8 squared, right? So I'm not going to actually break that down, just I'm going to show you this important fact that if you multiply a complex number with its conjugate, you actually get the squares, sum of squares of its imaginary and real part. So the original z was like this, 7, 8i. So you can try it out yourself. For example, if I write minus 3 plus 5i, this is our z, then z bar would be minus 3 minus 5i, and z times z bar would be minus 3 squared plus 5 squared, and whatever it comes out, okay. So this is kind of like our Pythagoras, if you can remember. So 7 squared plus 8 squared, it looks like our Pythagorean formula, and there's a connection to that. We will get to that later as well, but let's finish how we divide two complex numbers. Well, for this we multiply the dominator's conjugate number. Okay, so its conjugate is -5 minus 5i. We're just multiplying by 1, right? Nothing changed. But the fact is, if we multiply a complex number by its conjugate, we have -5 squared plus 5 squared, and on top you have two complex numbers multiplication, like 3 plus 2i times -5 minus 5i. And if you go through the calculation, it's going to be something like something plus something I. It's going to be still a complex number, but this is kind of slightly in a complicated way, right? So you have to do some calculations, but we will come back to a better way for multiplication and division. Okay, so if you can see that the addition and subtraction were very easy, but the multiplication and division was really bad. So let's make another point to that, how we can go to the same thing. So I'm going to bring out the z-plane diagram again. So we had 0 here, 1 here, 2 here, 3 here, -1, -2, -3. We have I, we have twice I, we have minus twice I, we have minus, sorry, I meant minus twice I and stuff, right? So we have arrowheads here. Okay, now we have seen that actually we can represent any value. For example, this value can be written as, this point can be written as 3 plus I, right? And as you can probably see that this length is actually, let me draw it in some way. So I guess I can just override this. So this red line is length, has length 3, and this line has length 1. Even though this is imaginary, the length is still a real number, and that's 1, right? So let me write the 3 here, and if we connect this point 3 plus I point from the origin, we create a right angle triangle. And what's the length of this triangle? What's the length of the hypotenuse of this right angle triangle? Well, it's root over 3 squared plus 1 squared from Pythagoras' formula, right? And we have seen that actually if this is our z, let me reuse green pen. If this is our z, this is actually z times z bar, right? So this is the modulus, this is also called the modulus of a complex number, okay, or sometimes also denoted as r, the radius from this point. So there it has a lot of name. So z, usually modulus is used as absolute value. So in real numbers, well, in real numbers we use modulus of a positive number, just a positive value. Modulus of a negative number is the positive value as well, right? So like if it's -3, we have 3. So you can interpret that as the distance from 0 in real numbers. So the distance from 0 to 2 is actually 2. So that's why the modulus is this distance is actually 2. But you can also say that, okay, the distance from 0 to -3 is actually 3, because, well, the distance has to be a positive thing, okay? Distance can't be a negative thing or a complex number for that matter. So this was basically, you can interpret modulus as distance of that point, the distance of -3 from our origin or 0th point. So that definition has been adopted here, that the modulus of a complex number is basically the distance from the origin, right? And this is also called r, for the fact that this is a distance r radius away from the origin. Okay. Next we are interested in this angle. So let me use another color. Let's call this angle theta. Okay. And let's analyze this position, analyze this triangle. So we have, let me match the colors. We have a triangle here, right angle triangle. Okay, let me draw it. Okay, so we have a right angle triangle like this. This is length 1, this is length 3, and this is length 3 squared plus 1 squared. Okay, and this is angle theta, and I'm not going to write it like that because these things will change. Let me write it as a parameter. This was a, this was b. If we write z equals to a plus bi, and this length is called the modulus of z, or r. Okay, so now can we write a equals to r cos theta and b equals to r sin theta? Can we write that? Well, we can, because we know that actually the definition of sin theta is the denominator will be the hypotenuse, so this is r, and our b here will be, so the opposite side of the angle will be here for sin theta, right? So this will be b, and so if we transfer this r to here, we will have b equal r sin theta. And similarly, from the definition of cos theta, a by r, we have a equals r cos theta. So instead of writing z equals a plus bi, we can also write this is r cos theta plus well, let's write the I here, I r sin theta, just not to get confused. Okay, so this is also another form of writing this in terms of well, if you can remember, this is like the polar format, expressing a point in terms of the distance from origin and the angle. And if you want, you can actually take common r, you will have r cos theta plus I sin theta. Now here's the most important part, I would say. Okay, so this is where your review of complex numbers stops, and we are going to introduce some new things, unless you have actually completed the complex number course. So this equation should actually ring some bells. Okay, you have cos theta plus I sin theta. That's the famous Euler's equation, the Euler equation. Okay, and that's also called the de Moivre's theorem, whatever. But this is a very important formula that's related to Euler, and that's that famous fact that e to the power I theta is equals to cos theta plus I sin theta, right? So for example, this is how actually complex power is defined. So for example, you might have heard that e to the power I pi equals to -1, and that comes from this identity. E to the power I pi equals cos pi minus plus I sine pi. So this is in radians, so obviously use radians if you want to use this formula. And the value of cos pi or cos 180 degree is actually minus 1 plus sine 180 degree is just 0, so we have minus 1. Okay, so this is the famous Euler's identity, right? And we can use this here to simplify our form. So we can say this is actually equals to r e to the power I theta. Okay, so that gives us a much more concise way to write. Okay, and we will actually use this format. Okay, so be very pay very important, okay, pay much attention to these details, because we are going to use polar coordinate systems, and we are going to write them like this. So in previous years you might have write it like r comma theta, but instead of that we are just directly going to write it as r e to the power I theta, because, well, that's the mathematical expression. And turns out that we can actually write z as that. So you can write z as a plus bi, or you can write it as r e to the power I theta. This is called the Cartesian format, and this is called the polar format. Okay, and this has some very useful cases. For example, multiplying and dividing one complex number with another complex number is very easy if you use polar format. So if you have any good calculators, like all of them has a conversion system from Cartesian or rectangular to this is also called rectangular system to polar system. Okay, so how can we do that? Okay, so first let's talk about the multiplication and division I was talking about in terms of polar coordinate system. So for example, 3 plus 2i, that's one way to write a complex number. Okay, then this is our z. Then we can say that our r is modulus of z, which is root over 3 squared plus 2 squared, and that is root over 13. So this is our r. And our theta will actually look something like this. Well, we have 3 here and 2 here. So this is our theta, and I guess you can say that, okay, theta is actually tan inverse 2 by 3 and some stuff like that. You can complicate things like that, but I am not going to complicate. I'm just going to call it some value theta. So you can say, okay, r equals to root over 1 by root 3 e to the power I theta, whatever that value is. Okay, that value goes here. So maybe it's just that degree. Well, so in electrical system we will actually use degrees. So for that I'm just going to use, like, maybe it's 35 degrees, right? But that's not the correct way to write. In fact, I'm feeling guilty. Let's write it in radian. So maybe it's 3 pi by 4 or something like that. Okay, so this is how we write our complex number in polar form and convert between one another. You can always use calculators. Okay, now what's so special about that? Okay, so for example, let's take two complex numbers, 3 e to the power I 3 pi by 4, and multiply that with e to the power so multiply that with 2 e to the power I don't know, some other angle, like maybe just pi, I don't know, it may be anything. Okay, and how can we multiply these two complex numbers? Well, this is very easy because all of them are already multiplied with each other, right? So you can just multiply 3 times 2, that is 6. And these two things multiplied becomes the exponent. So you know that e to the power x, or or anything basically, a to the power b times a to the power c is actually a to the power b plus c, right? The exponents gets added up. So if you add these things here, e to the power I 3 pi by 4 plus pi, right? And whatever you have here, so I can see that, okay, this is 7 pi and this is it. So this is your multiplication. So multiplication problem becomes very easy in polar format if you are given these two values, and this is what we will actually use. And also division problem gets much easier too. For example, e to the power I pi, so this is already divided by one another, so this is 3 by 2, so you have 1.5 your radius, and e to the power I, since we are dividing this time, so you have 3 pi by 4 minus pi. And if you do the calculation, well, if you take the LCM here, you will have 1.5 e to the power I minus pi by 4. Okay, so this way the multiplication and division problem becomes very, very easy, and we actually write the minus at the front of I just to make it obvious. Okay, so e to the power minus I pi by 4. Okay, so this is how we use complex numbers for multiplications and etc. And this is exactly why we are going to use polar formats here. Okay, so for example, so this is basically the review of complex number, and next we are going to start how we use it in electrical systems.